Qubits are the building blocks of the quantum computer. They tend to be noisy and decohere very quickly. We cannot rely on them to carry out the calculation for the amount of time that is needed.
Quantum computing nowadays can run up to 100 operations before it becomes useless. But in order to run a useful algorithm, we need up to millions and billions of operations. We need to manage the errors.
With quantum systems, things can go wrong and do go wrong all of the time. What quantum error correction does is it takes these unruly qubits and turns them into something useful. If you don't solve error correction, then you'll never have a useful quantum computer.
The basic principles of quantum error correction have now been demonstrated on a few different platforms, but it's not yet at the point where it truly is useful and is working well enough such that we can run deep quantum computations without the accumulation of errors.
To actually realize an error-corrected quantum computer is a tremendous classical engineering problem, and one that we're attacking full scale at Riverlane.
Back in 2014, I was at a conference and a third of the audience voted that there would never be a useful quantum computer. And so I founded Riverlane because I think they're wrong. Riverlane was founded in 2016. We're now up to 100 people, and we have offices in Cambridge, UK, and Cambridge, Massachusetts. We collaborate with many of the quantum hardware companies to add the error correction layer into their system.
My research group has been working on neutral atom quantum computing for the past 20 years, and starting from nothing, we've now reached the point where we're able to run quantum algorithms and circuits on the multi-qubit processor. At the same time, we've reached the point where it's become very clear that to make further progress, we will also need error correction. We're looking to do that in part through a collaboration with Riverlane. We're currently planning to test out some of Riverlane's hardware to use that as a springboard to an ongoing parallel development.
We're building fast decoders. We're building control systems that will scale to ultra-large numbers of qubits. We're working on quantum algorithms, and we're also working with hardware partners in co-design and analysis of quantum error correction experiments.
The thing standing between error correction and the qubits is the control system. Our control system is a software solution which can be portable across different types of hardware. Each one of our partners is unique. We work very closely with them, we embed ourselves in their teams, we learn as much as we can about their qubits. On the back of the control system, we have the decoder.
The decoder uses noise modeling and decoding algorithm flagging to the system that there's an error occurs and keep track of them. Ultimately, what we want to build is a decoder that can support a terraquark regime. We already have started building the future decoder, which is a decoder on chip.
So we also have a team in Boston in the US, and the Boston team is focused on understanding all of our hardware partners' qubits. So they do a lot of modeling of the noise inside these qubits, and this is really critical for us in helping us design the best possible solution for each of our hardware partners.
A long time ago, I was also a student working in a lab, doing experiments. We had to make everything ourselves. I'm really excited that Riverlane can help the labs and the startups and the scale-ups make the most of their qubits.
I think we've got the right people, we've got the right kind of skills, and we've got fantastic partnerships with quantum hardware companies. And so the prospect of us being a central part of the first error-corrected quantum computer is just amazing.